So hello everyone, my name is Francis O'Leary and today I will be presenting on the topic of subdivision surfaces. So subdivision surfaces, what are they and why do we need them? The original inspiration was to find a solution to problems that present themselves with patch-oriented solutions such as non-uniform rational B-spline or Bezier patches. The most prevalent issue with these solutions was that they had a tendency to have gaps at the borders between adjacent patches which yield a bad animation. So instead, we construct a uniform control grid from a control mesh and compute a functional limit surface. This way, when the control mesh is deformed, the resultant subdivision surface is also deformed, and since it is a uniform mesh, no gaps appear. So we kind of arrive at this perfect intersection of meshes and splines that yield a nice smooth surface that can be used for lots of applications. So moving on, the mathematical basis for why subdivision surface algorithms can form functional limit surfaces relies on the definition of splines and the reasoning behind curve fitting. Curve fitting and splines arise from the essential need to make smooth curves since simple geometric primitives only go so far. So we arrive at the topic of splines, which are piecewise polynomial curves that are defined by a set of control points. If an interpolating scheme is utilized, these control points will actually lie on the generated spline curve as seen in the example in the bottom left. Alternatively, if an approximating scheme is utilized, the points need not lie on the resultant spline curve and instead guide the curve. Since splines form the basis of subdivision surfaces, both of these schemes will play a large part in the algorithms we will look at later. Now that we have an idea of subdivision surfaces and splines, how did we arrive at this concept? In a sense, it all goes back to a conference at the University of Utah in 1974, during which the artist George Chaikin presented his curve generation method that is known as Chaikin's algorithm. The idea, which we'll cover more specifically in the next slide, is to take a closed 2D polygon and continually chop off the corners, so to speak, until a smooth limit curve is achieved. At this conference that Chaikin was presenting at was a man named Malcolm Sabin, who realized that Chaikin had effectively proposed an iterative way to generate uniform quadratic B-spline curves. Chaikin's algorithm is essentially a really quick way to generate smooth curves or forms from an input polygon. The idea is to begin with an initial curve or planar subdivision and then recursively subdivide the structure into smaller segments that more generally approximate the desired shape. The general process begins with an input set of control points. Given the control points, we then iterate through them and push them onto a stack. Once a new set of control points denoted Q and R in the figure to the right have been computed, the point is popped off the top of the stack, and the new points are added to a new data structure. The output then consists of the new control points that were generated at 1/4 and 3/4 of the distance between every pair of consecutive original points. These new control points are then concatenated to their neighbors to form the new figure. Thus completes a single run of the algorithm, which can then be repeated until our base case of a minimal segment distance has been reached. Just to really drive this topic home, since it forms the basis for many other subdivision surface generation schemes, here's an example on a closed input loop. You can see we have our input polygon with control points P0 through P4, and from there the first iteration refinement is computed, and we can see the addition of the new control points and their connection to exclude the original control points. Thus, if you begin with n control points, your resultant figure will have 2n control points. After the first iteration, we recurse and refine until a smooth limit curve is achieved, as is shown by the output polygon. So from Chaikin's algorithm, we arrive at the two main categories of subdivision surface generation algorithms that have been derived by many others after him. They are immediately derived from the definition we saw with respect to spline curves, so you can think of them in that way. For interpolating subdivision surface algorithms, such as the butterfly method, the original positions of the input control mesh will be in the output control mesh. The output limit surface is thus an interpolation between the generated control points and the original input control points. Algorithms that employ interpolating schemes often appear less smooth to the human eye, but give more control to the user, and features are less likely to be rounded off and lost, as shown in the image in the top right. Alternatively, for approximating schemes, the original positions of the original control mesh need not be maintained, and instead the original limit surface approximates these points. These surfaces, such as the one shown in the left, generally look more smooth, but sharp and small features may be lost. Thus, depending on your application, you may pick an interpolating or approximating scheme. Now that we have fully elaborated upon the necessary background information, we are ready to examine the big hitters of the approximating scheme world, which are Catmull-Clark subdivision surfaces and Due-Sabin subdivision surfaces. Both are centered along the same key notions and were presented in the late 1970s, but as you can see in the images on the left, they yield different results. So we'll begin by examining how the Due-Sabin algorithm works. This pseudocode shows the general process for one iteration, which takes an input mesh that describes a polyhedron P. The first step is for each face in P, we average all the points in the face. This results in the creation of the center points of each face, and we store them. Likewise, for each edge, we average the endpoints to find the midpoint and store each of these points as new edge points. Then, for each face in the original polyhedron, we cycle through their vertices and obtain the new face point for the current face and all the new edge points that are adjacent to the current vertex. All of these points are averaged, and we add this new point to our new polyhedron. After that, all that is left to do is form the edges and faces in our output polyhedron from just the new points that were created during this process. The general approach can be seen in the images to the right. We can see, for example, in the second iteration for the cube that the average points on the top face effectively shrunk it. That is, each side of the original cube now forms a smaller square. Each of these are now connected to form a more rounded shape. Interestingly enough, not many papers actually detail the runtime of the algorithm, most likely because the important part of these papers was the mathematical basis and validity for the algorithm itself. However, after conducting some basic analysis, we can see that the algorithm we just went over generates a new face at each original vertex, and new faces at each original edge, and n-squared faces at each original face. Thus, the dominant term is n-squared, and with the processing necessary for generating these faces, we can assert that the algorithm is big O of n-squared. As for memory usage, varying implementations utilize different data structures and may or may not operate in place. Thus, there are various options, and the memory usage is often determined by the application and its needs. Now moving on to Catmull-Clark, we have our general process outlined here again. Like Du-Sabin, we begin by finding the average point for each face. However, we begin to diverge from the Du-Sabin scheme on the next step, in which we average the endpoints of each edge with the average face points of the faces that are adjacent to the given edge. From here, for every vertex in our polyhedron P, we obtain all the face points that adjoin the given vertex, average them to be a number f, find all the edge average points that adjoin the vertex and average them to be a number e, and then take the barycenter of f, e, and the current vertex v and add it to our new polyhedron. Now that our average face points, average edge points, and new vertices have been added to our data structure, all that is left to do is finish the data structure by constructing its faces and edges. Thus, we see that this is very similar to the Du-Sabin scheme, but applies different weights to achieve different results. Here's an example of Catmull-Clark subdivision performed on a model of the Purdue P that I coded. The overall implementation is pretty much based on the linked source. This directly shows the process Catmull-Clark subdivision goes through, as we begin with the original shape with 34 faces, perform an iteration to obtain 136 faces, and so on and so forth until we arrive at 8,704 faces and a relatively smooth-looking Purdue P. I thought this was pretty neat, especially when compared with the original control mesh, and it really helped me understand how the algorithm works. Now for the actual analysis concerning Catmull-Clark. These figures are from 1993 but accurately display the runtime of the methods of the original algorithm. Note that the pseudocode we just went over generalizes the process and is great for understanding but would be slow in real life. Thus, computing the minimum energy mesh is often done by reducing the math to solving three linear systems. With this adaptation, using sparse matrix methods, the algorithm is big O of n-squared. As for memory usage, like Du-Sabin, there are various options, and the memory usage is often determined by the application and its needs, once again. So now we get to the fun part, which is how all of this geometry can be used in the real world for some really cool purposes. The first application we'll cover is interesting because it's not what I immediately thought of when I thought about subdivision surfaces. This paper comes from some researchers in Norway who wanted to tackle the problem of creating an accurate 3D model of the right ventricle of a human heart. This was challenging due to the complex nature of the right ventricle, which is an amorphous shape with some sharp edges. So they modified the Du-Sabin algorithm such that sharp edges are weighted and are preserved across recursive runs. And so in the future, this technique could be used to model other complex anatomical structures and glean more accurate knowledge from medical simulations. Switching gears, we go from medicine to engineering, where subdivision surfaces have been used to more accurately compute the effects of different stresses on different thin shell objects. This paper comes from Caltech, where they used an adaptation of the loop subdivision surface algorithm to perform structural analysis. Finally, we come to modern media, which I'm sure we've all experienced. Many video games and movies employ subdivision surfaces, and I couldn't even begin to scratch the surface of all the popular ones, so I listed some of the more well-known ones, from the Call of Duty series to popular Pixar movies like Toy Story 2. Something interesting about Pixar is that Edwin Catmull of the Catmull-Clark subdivision surface algorithm was one of their co-founders, and so Pixar has played a large role in introducing subdivision surfaces into animation in Hollywood, which has made a lasting impact on the industry. Lastly, here are some cool resources I found along the way, like some code to generate Chaikin curves and a Khan Academy website that lets you interact with and modify subdivision surfaces in real time. And Pixar's Open Subdiv library, of course. So thank you for listening. If you have any questions or comments, feel free to send them in the chat or email me at the address listed on the slide. Thank you. And here's a list of all the references I used if a particular topic happened to pique your interest.